Greetings, everyone. My name is Hernani Nascimento, and I would like to welcome everyone to the third presentation of the webinar series, Nowcasting Operations and Techniques, Perspectives for South America. This series is supported by the Nowcasting and Mesoscale Research Working Group of the World Weather Research Program of WMO, and we would like to thank all the individuals who have registered in today's talk. Because we have newcomers, I think it is interesting to say a few words about where the motivation for these presentations come from. The initiative for holding this webinar series was envisioned by a scientific committee in Brazil that is proposing actions to the weather services of that country to improve the forecasting of local convective storms. With time, this initiative grew to become a webinar series addressed to an audience that goes beyond the Brazilian national borders. So a number of professionals with long experience in research and operations in nowcasting of convective storms have been carefully selected to give these talks. Today's guest speaker is Burkely Gallo from the United States. Berkeley's talk will be followed by a Q&A session. And for that, we would like to ask the audience to place your questions in the Google Meet chat or in the YouTube chat. We will read your questions right after the presentation. So with no longer delay, I would like to pass the microphone to the co-chair of this session, Bruno, who will introduce our guest speaker. So Bruno, please, the audio is yours.
Okay, thank you, Hernani. And well, it's a pleasure to have Burkely Gallo here today. And she did her PhD in meteorology at the University of Oklahoma and her master's degree in meteorology at the Pennsylvania State University. And she is a research scientist at the Cooperative Institute for Severe and High Impact Weather Research and Operations, the CIWRO, which is formerly known as the Cooperative Institute for Mesoscale Meteorological Studies, the CIMS, and also at the NOAA's Storm Prediction Center. And Berkeley works with many research topics. We focus on applications of convection allowing models and ensembles to operational severe storms forecasting. And she is also a lead facilitator of the spring forecast experiment, NOAA's Hazardous Weather Testbed. So Berkeley, whenever you are ready.
All right, thank you so much, Bruno, and thank you to everyone for the invitation to join you here today. I was very excited to get this email and be able to talk with such a wide audience about some of the things that we're doing in NOAA's Hazardous Weather Testbed. So I'm going to go ahead and share my screen and we'll get started with the presentation here. As Bruno mentioned, I am an employee of the Cooperative Institute, so the University of Oklahoma. I'm not actually a federal person, just to have that disclaimer right up front, but I do work with a lot of federal scientists and forecasters as part of my work with NOAA's Hazardous Weather Testbed. So we'll be talking about that as we go through today and talking about the research and the operations and how we blend those two things together. So let's start out with a brief introduction to severe convective storm forecasting in the United States. And specifically, I'm going to be talking about the role of the Storm Prediction Center, which is the national agency that is in charge of severe convective storm forecasting. So the Storm Prediction Center's timescale that they're concerned with is largely from the next few hours all the way out to 8 days. So it's a pretty broad range of time that SPC is concerned with. And I'll be using Storm Prediction Center and SPC interchangeably as we go throughout this talk. One of the flagship products of the Storm Prediction Center is their convective outlook. And the convective outlook is displayed in these two images here. The convective outlook for day one, or the current day, is updated and issued 5 times per day. And it is also issued at day 2, day 3, and then days 4 through 8. So there are convective outlook products that span day 1 through day 8. These convective outlook products cover the hazards of tornadoes, hail, and convective winds. So something that's a little bit different in how the United States does things relative to some other countries is that we actually do not include flash flooding in our definition of a severe convective storm. The flash flooding aspect of things is handled by the Weather Prediction Center, which is headquartered in Washington, D.C. And they actually also do have their own hazard HMT, the Hydrometeorological Testbed experiment, covering elements of this flash flooding. So we won't be talking about flash flooding today. We'll be talking about tornadoes, wind, and hail. And these forecast categories that you see on the left-hand image here of anywhere from marginal to slight, enhanced, moderate, and high, as we go from lower to higher, are backed up by these underlying probabilities. So on the right, that's the underlying coverage probability of a tornado within 25 miles or 40 kilometers of a given point. So it's this coverage probability. The coverage probability of tornadoes in this case is what's driving this high risk area, or that hot pink in the middle. But there are also wind and hail probabilities that are underlying the outlooks as well. So these underlying probabilities of the individual hazards are what drive those categorical outlooks. I did also want to show this graphic that has recently been redone and introduced by the National Weather Service. And this shows the different categories of the severe thunderstorm outlook. So we go all the way from the lowest one of marginal up to the highest one of high. And this graphic really explains the different details of what sorts of storms you can expect, the coverage of those storms, and the severity, as well as on the right-hand side, having a definition for what we use for severe wind, severe hail, and significant severe wind and hail, which is really another level of intensity beyond just your regular severe weather. So that describes the convective outlooks. Other products issued by the Storm Prediction Center include severe thunderstorm and tornado watches. These products are issued on an as-needed basis by SPC forecasters in collaboration with their local weather forecast offices. So as opposed to the convective outlooks, which are issued on a set schedule, the tornado and severe thunderstorm watches are as needed. So you're not necessarily going to have one every single day of the year. The goal for these is really to issue prior to the development of severe thunderstorms and tornadoes to give people lead time and the ability to make preparations for severe convective weather that could be headed toward their area. The criteria for a tornado watch is that we expect 2 or more weak or brief tornadoes or 1 significant tornado within the areas of the watch bounds. And for a severe thunderstorm watch, the criteria is that we expect 6 or more events of an inch or greater hail or damaging winds of 50 knots. So you really want to have more than just an isolated incident of hail or wind. These watches also have associated probabilistic forecasts with them. So you can look and see the different probabilities of 2 or more tornadoes, strong tornadoes, and it's broken down by the different hazards. So this information that is probabilistic is also tied to these watches. The final product that folks are most familiar with on the severe convective side of the Storm Prediction Center are our mesoscale convective discussions, or the MCDs. And mostly these consist of a graphic with a main message in the text box. As you can see here, we've got 2 different text boxes, and then a detailed discussion below that really dives into the nuance of the meteorology of the situation. Most of these discussions are focused on mesoscale areas of enhanced potential for severe weather. So where are we looking in terms of storms for the day? Traditionally, these are somewhat large scale. They can be roughly watch size, maybe a little bit smaller than a watch, but the one that I have shown here does cover nearly all of this state of Mississippi. So they're relatively large. But we have also, as we've gotten to know more about the science, we've been able to hone in on smaller mesoscale discussions in more recent years that highlight enhanced corridors. So this particular mesoscale discussion is focused on the evolution of a storm or two and its tornadic potential out the next couple of hours. So it's really looking kind of at that low end of the overall time scale that SPC is interested in. These mesoscale discussions can highlight not only our expectations for a watch, so is there one area of the watch that's looking a little more threatening at the current moment? Is there another area of the watch that in a few hours we expect more development? Or just expectations for even issuing a watch. We have some that come out before a watch is issued that gives a probability that a watch will be issued at all. So they really are meant to highlight and explain meteorology behind these products. So that sums up the SPC's products on the severe convective weather side. We also have a suite of fire weather products and some winter weather mesoscale discussions, but those will not be the focus of this talk. More the focus of this talk will be convection allowing models, or CAMs, and convection allowing ensembles. So the image that you see here is a 500 millibar height from the United States operational convection allowing ensemble, known as the HREF. Of course, these models are just one tool in our forecasters toolbox. They're considering their observations, our satellite, radar, the mesoanalysis, as well as the global models. But the convection allowing models are a unique tool that forecasters can bring in once they have their mental models created to help understand exactly how a day's storms may evolve. CAMs can really provide this insight into convective storm initiation, coverage, and intensity because their horizontal grid resolution is usually on the order of 3 kilometers, which allows for the convective parameterization to be turned off. So we're able to depict these sorts of convective features. The image here is a simulated reflectivity image from a convection allowing model. And so you can see how realistic this radar image looks. I mean, it looks quite similar to an actual radar image. So you can get an idea if you're going to have individual cells, if you're going to have a line of storms, and what sorts of associated hazards those may have. Currently, the United States has an operational convection allowing model known as the HER that goes out every hour to 18 hours, and then every 6 hours, it goes out to 48 hours, as well as an operational CAM ensemble that runs and updates about 4 times a day, and that is the HREF. Another thing that we can get out of these CAMs and CAM ensembles is known as Updraft Helicity, or UH, and that's now what's depicted in the image on the right. This is the only equation in the talk, and it depicts what updraft helicity, or UH, actually is. It's just the integral of the updraft speed and the vertical vorticity over a specific layer of interest. Typically, the layer of interest that we use is the 2 to 5 kilometer layer because that really reflects our mid-level mesocyclone and enables us to determine if a storm in the model is rotating or not. Previous studies have found that this 2 to 5 kilometer UH corresponds really well with severe reports of tornadoes, wind, and hail collectively. And since we're not really able to model these processes directly on such a large scale as the United States, we just don't have that resolution at the moment, we have to use these sorts of proxies to determine where severe weather is likely. So speaking of the HREF, I'm going to jump in a little bit to our O2R, R2O, and talk about how this was really a success story for operations to research and research to operations, which is what that acronym stands for. Essentially, early on in the HREF process, we had all of these deterministic convection allowing models, but they weren't really in an ensemble format. They were just individual runs. And so all of these available deterministic CAMs were processed together as an ensemble at SPC. And this was known as the Storm Scale Ensemble of Opportunity. Ensemble of Opportunity because we saw the models there and assembled them into an ensemble. It wasn't a formally designed ensemble. This ensemble really tested well in the Hazardous Weather Testbed for many years. So we asked participants subjectively their thoughts on different ensembles. And the Storm Scale Ensemble of Opportunity here is on the left in the blue bar. And then formally designed ensembles are the rest of those ratings. And you can see the blue bar is pretty far up there. So not only subjectively, but objectively, when we went in and looked at some different measures of forecast skill, the SSEO was doing very well. So after a few years of testing it, the SSEO became operationalized as the HREF, or the High Resolution Ensemble Forecast System, in November of 2017. The HREF has gone through a few iterations now since 2017, and our current version has 5 different convection allowing model runs, and then also uses time lagging. So it has 10 total members that are processed, post-processed, and some of that displayed output can be found at the website on these slides. So I've talked a lot about SPC and where they fit in. You might be wondering, where does the National Severe Storms Laboratory, or NSSL, fit in? NSSL is a research lab that is focused on severe convective storms and hazardous weather problems. So they conduct basic research on severe storm processes through field work, field campaigns, modeling, all sorts of different ways to conduct this research. But they also conduct operationally relevant research in the test beds and working with forecasters. And that's the world that I move in mostly. We also have a relatively new unit within the National Severe Storms Lab that's focusing in on social science and how people can best use the information that we're providing them to protect their lives and property, which is that NOAA mission. The co-location of SPC, NSSL, the Cooperative Institute that I work for, and the University of Oklahoma, it really allows for a lot of collaboration and a lot of cross-pollination of ideas and enthusiasm. So I think it's a very unique environment and allows for a lot of good ideas to kind of percolate both ways, from research to operations and from operations to research. One of the main collaborative activities between SPC and NSSL specifically is this collaborative execution of spring forecasting experiments, which is the flagship experiment of the experimental forecast program in the Hazardous Weather Testbed. So let's talk a little bit more and pivot towards the spring forecasting experiments. First off, we'll start with what is the Hazardous Weather Testbed? The testbed is a specifically designed space for practitioners and researchers to come together. So this image was taken from a busy day in May, either 2018 or 2019, when we had two concurrent experiments ongoing in the Hazardous Weather Testbed. The testbed is this physical facility. Through the glass on the right-hand side, that's the operational center of the Storm Prediction Center. Through the glass on the left-hand side, that's the local Norman Weather Forecast Office. And the two experiments in the testbed at this time are serving really those clientele that are through the windows. So if people need motivation, they can just sort of look up and see the folks who this work will be helping. I'll be talking mostly about the experimental forecast program, which is concerned about those scales that are a few hours to a few days in length. And the experimental warning program on the other side is concerned at a bit shorter time span. So really the current moment out to a few hours for the most part. And bringing people together like this really does accelerate that transfer of research to operations. You get the communication, you get people talking, and you kind of understand where the needs are from both user groups. So the testbed is home of annual spring forecasting experiments and many other experiments throughout the year. And while it looked like this in 2018 and 2019, for the last few years, the Hazardous Weather Testbed has looked a little bit more like we look now in a Google Meet presenting. But the spirit of the testbed is definitely still there, and we are able to still get a lot of that collaboration. So speaking specifically of background on the spring forecasting experiment, this experiment has been going on a while. This is something that has been built up over many, many years. It formally started in 2000. And so this is an early picture of one of the experiments that was pre the Hazardous Weather Testbed, since we did not move into that space. The space didn't exist until the mid-2000s. But the emphasis has always been these research to operations and operations to research problems. Our experiment occurs real time, which is a little bit different than some of the other experiments that are focused more on retrospective cases. This creates a time pressure for our folks to issue their products. You know, those of us in the research and the academic world may not be as familiar with the time pressure that the operations folks have when they need to get a product out. They can't just sit there and digest every single piece of available data because it's too much data to make your product on time. And nobody knows the answer in advance. So I walk in as a facilitator, not knowing necessarily what the day's weather will bring, much like the participants. And that really adds a sense of urgency and fun to our activities. It also means that we're looking at a variety of cases. This experiment spans 5 weeks in May, so the heart of the spring convective season in the United States. Some days are not as high end. You know, we're maybe looking at a few wind reports across Texas here in this case, but, you know, not really a ton of severe weather. Other days, we are expecting a major tornado outbreak across part of the country. And while these two images focus on the southern plains, our domain does move across the United States to cover wherever severe weather is that day. So we will frequently be in the Northeast or the Mid-Atlantic or the Northern Plains. We move all over the country, wherever the severe weather is going to be. And all of this fosters all of this demonstrates new tools to our forecasters. So the forecasters are able to see what's coming down the pipeline in terms of research ideas. They're not just going to have a product show up one day and not have had any exposure to it. They'll learn its failure modes, some of its strengths and its weaknesses directly from the researchers themselves. And it also fosters discussion and collaboration. So researchers can work in that feedback and iterate their products to really make them the most useful products that they can. This has happened even virtually. So we have had 3 years now of virtual spring forecasting experiments. These started in 2020. We pivoted about 6 weeks prior to the experiment from a in-person to a virtual experiment once we realized the extent and the severity of COVID-19. And in that first year, we did have limited activities. So most of our participants only took part in the evaluation activities, but our National Weather Service participants were able to conduct full forecasting activities. And on the right there is a drawing tool interface that forecasters could use to draw experimental forecasts. We brought back these forecasting activities for all of our participants in 2021 and 2022. So we were really able to get the evaluation and the forecasting components of the experiments working. In 2022, we iterated again and added a lunchtime science panel once a week with developers of different guidance to allow our participants to get more of an in-depth look at some of the tools that they were testing. We ran things in 2 sessions with multiple activities per session. We usually had a morning session from 9 to 12:30 Central Time, and then an afternoon session from 2 to 4. And it's important to note that each of these virtual experiments incorporated new things. We didn't just take our in-person experiment and duplicate it in a virtual framework. We really iterated and added new activities as we went through. We also figured out a lot of things along the way and ways to make virtual work. So some of the things that we did, the crucial was thoughtful and thorough web design and testing out the tools that our participants would use as they were going through their daily activities. We also increased the number of facilitators so we could break people out into smaller groups, have a little bit more discussion, and have things like our retired SPC forecaster, Dave Imey, who came back. He was still drawing his hand-analyzed maps and presenting them to the groups. So we really had a large number of facilitators who could take care of a variety of different things. We also had a background communication interface. So if there was something going on and one of my participants told me, hey, I can't access this data, I could go into the background communication interface and ask someone who's on the back end of things and is not participant facing if they knew what was going on. And frequently they were able to fix things extremely quickly. And this really helped things run smoothly. We also worked in a variety of screen breaks and independent working time where we told people, turn off your cameras, mute yourselves. If you need to stretch, please go ahead, but we will be here if you need anything. And that allowed people to not have as much Zoom or screen fatigue because it really is tiring and taxing to be on a virtual meeting for 8 hours a day. We also picked up the involvement of our participants via votes and polls and some of those other tools that you can get in Google Meet. So we would ask people, oh, do you think we have a 10% tornado contour today? And instead of having to speak up, they could just raise their hands in the Google Meet tool. So we were able to get a lot more interaction that way. Our specific schedule for the 2022 spring forecasting experiment is shown here. We had a block of evaluation activities in the morning, and then one group did an evaluation activity in the afternoon. And then we had several blocks of forecasting activities. So we had people evaluate these experimental products, but also use the experimental products to generate forecasts and take those kind of one step further than just evaluating them. Essentially, our flow of things was we first asked, what happened yesterday? What did the storms do yesterday? We then went through and looked at our guidance that we had and the forecasts that we had made yesterday and completed evaluations to see how good the guidance was performing and how well we did it also. We then got all back together and looked at what was going on at the moment and what we anticipated for the next 3 days, because our next activity was to issue a convective outlook forecast, an experimental convective outlook. We did this for 2 groups for the first day, and then we had 1 group doing day 2 and 1 group doing day 3, and they were issuing hail, wind, and tornado forecasts. Then we had our lunch break, and that, as I said, had a panel discussion once a week, but besides that, it was kind of time for people to refuel, get some food, and catch up on anything else they may need to take care of. We got back together after lunch to see how things had evolved and got another forecast briefing. And then we entered into the afternoon, which was largely our short-term forecasting activities. So everybody did a short-term forecasting activity from 2:15 to 3 p.m. local time. And then most of the groups, 3 out of 4, did another short-term forecasting activity from 3 to 4. However, this year we did incorporate a new element, a focus group discussion, where folks could give their thoughts on a new forecast type. So that was something exciting that we worked in this year. As far as our guidance goes, we usually have a number of models that are contributed by various agencies to spring forecasting experiments. So to be able to handle all of this, we developed something called the Community Leveraged Unified Ensemble, or the CLU. And this was really inspired by a recommendation to provide evidence-based decision-making so that the US could have the best possible for future convection allowing ensemble. And so what was happening essentially is that we were getting more and more models over time. This is the number of models versus the year from different contributors. And while we were, of course, appreciating all of these contributions, sometimes they were coming in on different grids or they were having different fields in them. And it was hindering our ability to make these apples to apples comparisons between different groups, which is something we really wanted to do. So starting in 2016, we established the CLU framework to organize contributions from multiple agencies. And this allowed for us to have more controlled experiments where only one thing would be varied between the different groups or the different agencies. Everyone contributed a standardized grid and set of output variables. And this allowed for not just those more one-to-one comparisons, but also easier visualization and post-processing as we took in all of these different data streams and went to display them. So as you may be guessing, the spring forecasting experiment itself is really a large umbrella that contains a variety of experiments within it. So on this next slide, I've got all of the different things that we explored just in the 2022 experiment. So our CLU experiments included things like testing different ensemble physics schemes, testing different aspects of data assimilation, ways to configure our future convection allowing model in the US, testing new iterations of the model versus our current operational standard, and testing things like the different parameterizations and stochastic physics. So lots of different tests were going on within these clouds. We also tested things outside of the CLU, one of which is calibrated guidance strategies. So these are different methods of creating first guessed wind, hail, and tornado outlooks. We also tested the Warn-On forecast system. We've been working with that experimental ensemble since 2017, and I'll get into what exactly that ensemble is a little bit later. But we tested the impact of how many members that ensemble had and how time lagging affected the forecasts. We also had a version of one of our models where we had a high horizontal grid spacing, and we wanted to see if that benefited the forecasts of any of our severe convective hazards. We tested our different analysis systems. So looking pre-convectively and around the storm, if we could get these good analysis systems working and just, what's the best method for developing these sorts of systems. We also had a watch guidance product that we tested for the first year in 2022 that essentially gives forecasters a first guess for where a convective tornado or severe thunderstorm watch could be and when it would be during the day. So we wanted to see how well that algorithm was performing. We also had a few machine learning aspects, not just in the calibrated guidance or the threats in motion watch, but also in things like our severe wind probabilities or convective mode probabilities. So really applying machine learning to all different aspects of severe convective forecasting. And then finally, we had an ensemble subsetting experiment where we were testing if an ensemble sensitivity analysis could identify a subset of ensemble members that was more skilled than the full ensemble. So as you can see, we had a lot of different experiments. We generate a lot of data. And so we have this 5-week period where we're conducting the experiment, collecting our data, but much of our off season each year is spent diving into these data sets, along with several of our contributors and our collaborators. We're able to explore a variety of these questions in the off season. So let's talk a little bit more about the forecasting activities and experiments that we do. We'll start with those, and then we'll talk about the evaluation activities afterward. So one of the things that our participants use is the forecast drawing tool. This tool was developed by Brett Roberts, one of our facilitators with a lot of web design expertise. And this framework allows participants to look at this experimental model guidance underneath and draw their experimental forecasts over the guidance. And then those forecasts are saved as a JSON file format. So our participants draw these forecasts with the web-based tools. Most of the time, they're drawing probabilistic forecasts over different time ranges, whether that's the entire day or for an individual hour. But we do have some functionality for other types of forecasts. And people can issue their own forecasts with these, or we can forecast as a group. And you can see there are a variety of experimental fields that can be looked at behind the drawing that you're doing, not just the storm attributes from the convection allowing models, but also environmental attributes like what is shown here. And you can look at different ensemble guidance as well. So one of the things that we were looking at were these experimental conditional intensity forecasts. And this is another R2O, O2R type activity that we were looking at. If we think back to our convective outlook products, you may have noticed in some of those figures I showed earlier that there was this region that was a black contour with hatching in it. And that currently represents a 10% or greater coverage probability of significant severe weather. So that large hail, that very intense wind. But our SPC forecasters are already discriminating between high impact and low impact events. We really only have that one hatching contour currently. And so we can only really express one thing. But from 2008 to 2017, these statistics here generated by Andy Dean show that the percent of significant tornadoes increase as those probability categories go up. So the forecasters are able to discriminate between having these high impact and low impact events and when we're going to maybe get a lot of significant tornadoes. So what we wanted to do was introduce a new layer to the outlook focused on significant severe. So we would have that coverage probability, but also conditional intensity. We've tested these experimental forecasts since 2019, and the conditional intensity forecasts were actually the subject of our new focus group activity in 2022. So we're shifting somewhat from, can we draw these sorts of forecasts and create useful information to how are people going to receive this information and use this information to help themselves? So this is an activity that took place in the HWT. It's now moving into some more operational testing, and we will see where it goes down the line. I also said I would talk about the WMO forecast system. This ensemble is something that we use to do our experimental forecasting activities in the short range, because this CAM ensemble is a short range CAM ensemble. Essentially, we've got 18 different members in this ensemble, and it issues forecasts at the top of the hour out 6 hours, and then at the bottom of the hour out 3 hours. So you're essentially getting new data every half an hour. And the data has high temporal resolution. So as you can see in this animation, you're able to see every 5 minutes what the data is doing. So it really gives you a lot of information. The WMO forecast system is different from a lot of other ensemble systems in that it really has this high temporal frequency data assimilation. So it's assimilating radar and other data every 15 minutes in order to give you a good picture of what individual storms are going to be doing. It is also on a somewhat limited domain, a regional domain, relative to some of our other ensembles, covering a few states. The system is run daily during the spring in conjunction with the spring forecasting experiment. We decide the domain placement each day, but it's also occasionally run for other events like our Southwest monsoon. We have run it for different hurricane landfalls, occasionally aviation concerns. There are a variety of different ways that we're testing this new ensemble. And it's really the name Warn On Forecast comes from the initial idea that we're going to be able to issue warnings based on forecasts from this system rather than by detecting something on radar. So we really want this system to be able to distinguish forecasts from maybe two storms that are right next to one another, to extrapolate those different storms out and provide some storm scale guidance. So how we used this in our 2021 and 2022 spring experiments, one of the ways was by participants issuing their own mesoscale discussions. So they used the Warn On Forecast system, other available guidance, and their observations to create their own mesoscale discussions, and then they had to share them with the groups. So you would get things that looked like this, where folks would draw over some of the experimental guidance and then highlight different things like an outflow boundary or an MCS, different convective modes. Some people drew over simulated or observed radar and then also appended additional fields onto their mesoscale discussion. And some people drew over observed radar. So we got a variety of different mesoscale discussions for each different day that we were conducting the experiment. And we do ask people for feedback after the spring forecasting experiment each week and look at that feedback to try to iterate and make things better. And this activity was super popular with participants in the post-experiment surveys. They really felt an appreciation for the process that SPC goes through when they're generating their mesoscale discussions. And I think it increased their investment in the activities because they had to create and then present a product to the rest of the group. And for some folks, this may be the only forecasting that they do all year. So it really is kind of getting them out of their comfort zone for some people. From a facilitation standpoint, I really like it because it allows us to see what aspects of the guidance people are using. What are they drawing over? What is captured? What things are they noting? So it's really interesting data for us to have. Half of our participants each day completed this activity. The other half of participants issued hourly probabilistic forecasts. So seeing if we can issue probabilities at these pretty small time and space scales. So an example of these forecasts is currently shown on the screen. We further divided participants into two groups in two different Google Meet rooms. One group was able to use the Warn On Forecast system in 2021, and one group did not use the Warn On Forecast system. So we really wanted to see the added benefits of this experimental ensemble. We also divided it into our individual expert forecasters, which were our operational forecasters, people who do this as part of their daily job, issuing forecasts. And then all of our other participants, the model developers, the academics, the researchers, they had their forecasts aggregated into a consensus forecast. So it was kind of a wisdom of the crowds type forecast, and we were able to compare these. In 2021, they issued two initial forecasts, then they updated those two initial forecasts and issued one extra forecast. So how did these forecasts turn out? Well, here's an example of one of the consensus forecasts. The probability contours are those colored contours. Hail reports are in green and significant hail reports are in the black dots. And on the bottom is a practically perfect forecast, which is otherwise known as the forecast that a forecaster would have drawn had they known exactly where the reports would have occurred beforehand. So if we look at the subjective ratings of these forecasts from the next day, the difference between the Warn On Forecast system folks and the no Warn On Forecast system folks was really clearest in the expert forecasters, or the more saturated colors on this image. WAFs improved the rating of all of these different hazard forecasts, but the differences in the ratings actually were not significant when we put them to the test. Consensus forecasts generally fell in between the no WAFs and the WAFs forecasts, And so we're wondering if this is sort of a wisdom of the crowds effect that we're seeing. And the consensus forecasts look pretty reasonable throughout the experiment. In 2021, we were honestly not sure how these were going to look, so we considered it a big win that they did look very reasonable. As for how these forecasts performed objectively, we've been able to do some analysis on them after the experiment. This is a rock diagram that shows the probability of detection versus the probability of false detection. The forecasters who were using the Warn-On forecast system aggregated across all 5 weeks is the solid line, and then not using the WAFs is the dashed line. And so what we found is that using the Warn-On forecast system improved the forecasters' probability of detection, especially at these lower 2% and 5% thresholds. People were able to capture more of those tornadoes. This also didn't greatly increase the probability of false detection. So they were kind of staying in roughly the same spot on the x-axis, which is good. We don't want the false alarm or probability of false detection to increase. So what we were seeing is that the expert forecasters who were using the Warn-On forecast system were able to capture more tornadoes in their contours without greatly increasing the false alarm. We saw this similar effect across hazards and hours. This again is our tornado forecasts. And in this diagram, the upper right-hand corner is better. And again, you see the Warn-On forecast system forecasters performing better. But the effect really was largest for tornadoes. So that's the one that I'm showing as an example here. When we look at the fraction skill score, here is the plot of the fraction skill score for each forecast hour they issued. The W is the forecasters who are using WAFs. The N is the forecasters who are not using WAFs. What you see is that the W is higher than the N at every hazard and every hour, except for this initial 22 to 23 UTC hail forecast. The trends in time differed per hazard. It wasn't like as we got later in the day, one forecast got better, or the forecasts always improved. But it's also important to understand these are using relatively early Warn-On forecast system forecasts. So the Warn-On forecast system doesn't run the entire day. We start at 17 UTC, and then our last forecast is issued at 3 UTC. The cycles that our participants were using were right around 18 or 19 UTC. And the Warn-On forecast system's strength really is in its ability to assimilate ongoing storms and extrapolate those out. So if we were looking around the time of convective initiation, the Warn-On forecast system forecasts are not necessarily as good as they would be if the storms had been ongoing. So we have work in press right now that looks at the storm longevity and actually quantifies how much better WAFs gets the older the storms are. So I really do think that these results that we're showing here with the improvement are kind of a floor for the improvement. And there's actually a potential to see a much larger impact from the Warn-On forecast system than what's demonstrated here. As far as the consensus forecasts, evaluation of that is underway, and hopefully those results are planned to be presented at some upcoming meetings, but that is not quite done yet. So how did we change this for 2022? For 2022, we, instead of doing a WAFs versus a no WAFs, did a set of people who had access to WAFs and a set of people who had access to WAFs and this machine learning guidance based on the WAFs. So that's what's pictured here. These are object-based probabilities that a report will occur within one of these objects. So that's what that number refers to. There was separate guidance for each of the different hazards that was looked at, so tornado, wind, and hail. And we worked with the developers of this product for multiple years. So in 2021, they had this product in as an evaluation exercise so that participants could give feedback on the display and on the functionality. They took that back, iterated it, and then we were able to use it in our forecasting exercise in the 2022 spring forecasting experiment. So much like we did before, we had one group that used WAFs without the machine learning, one group that used WAFs with the machine learning, and then our individual expert forecasters and our consensus. And the black box here outlines the Warn-On forecast system domain because it is a little bit smaller than our typical SFE domain. For this year, we issued 2 initial and 2 final outlooks. And analysis of those outlooks is currently ongoing, but I can say that participants found the machine learning guidance to be very useful and very helpful for all three different hazards. So at least from the subjective evaluations, it really does seem like this guidance added something above and beyond the WMO forecast system, but objective verification is also underway. So those are some of our forecasting activities. Let's also next talk about our evaluation activities and experiments. So for these subjective evaluations, I do have a few notes on our sources. So we have a variety of different data sources that we use, and that's because when we're looking back at yesterday's weather, it's entirely possible that not all the reports have come in. So we'll look at simulated reflectivity from the model in the top panel here, and observations in the bottom panel. But then we'll also look at preliminary storm reports. So in this figure, the red inverted triangles are tornado reports, the blue squares are wind reports, and the green circles are hail reports. So we're able to look at those LSRs. But those reports aren't always in the next day, particularly when it comes to the tornado reports. So it takes time to go out and survey the tornado damage, determine if it was tornado or straight line wind damage. So some of those reports just aren't quite there. So we supplement some of this with MRMS mesh data, which is a radar-derived maximum estimated size of hail to try to get an idea of where the radar is indicating hail. We also supplement with National Weather Service warnings. And so these are issued by those local WFOs, and they are much smaller scale, but essentially we use them as an expert forecaster thought that there was a significant enough chance of severe weather that they issued a warning. We also use our observed composite reflectivity. And then when we're looking at temperature and dew point and other environmental fields, we use our RTMA analysis fields. Now that's for our subjective verification. When we go back and do our objective verification, usually it's a few months later. And so those reports have had time to come in. And so we use the storm data reports. And we often consider more fields in objective verification than we do subjectively because we have a limited amount of time in each day of the experiment. So this is what two of our model evaluations would look like. The one in the back with the simulated radar, that's how we evaluate a lot of our deterministic products. And then the one in the front with the Updraft Helicity is how we evaluate a lot of our Ensemble products. So we're looking at composite reflectivity in the background there, comparing that to observations. And then we're looking at the co-location of the reports with these probabilistic contours indicating the probability of UH over a certain threshold. Now this year, our models were blinded whenever we first looked at them. So when participants were filling out their surveys, they didn't know which model was which. They only knew them as model A, B, C, and so on. And so we also switched the panels around day to day. So where one was the previous day, it wasn't necessarily the next day. But we unveiled the names of the models whenever we were actually doing our discussion so participants could see which model was which. And we did this to eliminate any bias that some of the models may have or previous associations with the models. And we had them rank the models from best to worst this year. So for some results here, actually the lower the bar in this top figure, the better the performance. So we were able to see our current operational ensemble, the HREF, was still performing the best, but the RRFS P2E, which is one of the candidates for replacement of the HREF, is also performing quite well. So we had one evaluation where we dove specifically into these two ensembles. And in directly comparing them, we saw that the HREF was clearly better for temperature because of a cool bias in the RRFS. The HREF was a little bit better for UH, but really those were pretty similar. And then the RRFS was better for dew point because HREF had a dry bias, especially early in the forecasts. And that also impacted the forecasts of the Cape. So we're able to drill down into specific severe convective weather parameters and assess these models and ensembles from that severe convective storms perspective. We did something similar on the deterministic models comparison. For this display, on the left is better, on the right is worse. So we've got our highest to our lowest, and that's true for both of these panels. And when we look at our composite reflectivity, simulated reflectivity, and our UH for our deterministic models, we see the HER, our current operational model, And then the RRFS models, our 2 experimental models, all performing pretty similarly for reflectivity and UH, although the HER most frequently was ranked the highest. So it has the highest count in that number 1 bin. 2 of our other experimental models were not quite ranked as highly, and we need to dive into those comments and see exactly why. If we look at more environmental fields, so temperature, we see that the HER, again, is performing best, and it's not quite as close with this environmental variable because of a cool bias noted in the RRFS models. So these are some of the results that we get when we're doing these side-to-side comparisons of different models subjectively. Our final piece of subjective evaluation that we do is our calibrated guidance. So calibrated guidance frequently is looking at different first guess fields that are developed for forecasters. So in this case of these 5 different types of guidance, we're looking at first guess tornado probabilities for forecasters. And then the reports are overlaid, and the practically perfect is in the lower right, and the practically perfect is a little low because we didn't have all of these tornado reports at first. Typically, these pieces of guidance use the same ensemble baseline. Mostly it's the href, and it's really just the way that the guidance is formulated that differs. So we're trying to figure out what different ways work the best. We compare to the practically perfect fields with the LSRs, and I've already talked about how that can be a challenge. And we're really able to assess the different forecaster priorities. So are they sensitive to the probability of detection? Are they pretty sensitive to not having big areas of false alarm? We're really able to get at that through these individual responses. So I'll also touch quickly on a calibrated guidance and R2O success that we've had from the spring forecasting experiment. My PhD work was originally, or ended up being in developing some of these guidance tools for forecasters. So I started out just taking raw fields from the models and from the ensembles and trying to create probabilities based on those. And I had those in the spring experiment in 2015. I got a lot of feedback in the 2015 spring forecasting experiment. I also got some input from some SPC forecasters, and they were all saying, well, these probabilities are relatively high. So the forecasters said, hey, we've made this data set that has the probability of a tornado given a right-moving supercell. Would you want to utilize that? And I said, yes, absolutely. So using that, I developed a new tool. And so the old methods are panels B, C, and D here, essentially the panels that have these blue areas and a lot of hot pink. They're pretty intense and high probabilities. The upper left-hand panel is the SPC forecast for the day. And then the very bottom panel is this new methodology that I used that I developed based on the forecaster data set and the model output. So you can see it's much lower and closer to the SPC forecasts. This got tested in the spring of 2018 in the spring experiment and published in April 2018. So I got that input, and then the methodology I had developed in a different ensemble. I ported it over to the href, and it was implemented on the href public-facing site in November 2017. So if you go to the href webpage and you look under the SPC guidance tab, that 24-hour STB calibrated tornado circle guidance is there on a daily basis, twice a day. So these probabilities iterated through the testbed for 2 years prior to implementing in 2015 and in 2017, and now they're used as a baseline for other tools and other guidance. So calibrated guidance that performs well and iterates through can be transferred to this public SPC page to be more broadly utilized. And we also have an internal site where we can test this guidance as well. So I think it's a really unique story of a success. I'll wrap it up here with just a quick few slides on the potential future directions for the spring experiment and where we might go in the future. We do want to blend these virtual and in-person components. So for our virtual experiments, we were able to realize the tangible goals of each experiment, but we did really miss those intangibles and spontaneous conversations that happen when people are together in the same room. We were able to have interaction and discussion between our participants, and I actually think the chat functionality is very beneficial because folks who are a little more quiet or may not want to speak up can type their thoughts instead. But you have to craft those discussions quite carefully to get people to speak up and to elicit that feedback. We were able to get more participants from people who might not be able to easily travel for an entire week. That could be people who have care responsibilities at home, but it also was valuable for a lot of international participants. So we had people joining us from Australia, Canada for the first time, the United Kingdom. And last year we had some folks from the European Severe Storms Lab. So, as this webinar demonstrates, you can get a very global reach and you can actually interact with folks who you might not be able to otherwise in the virtual space. And that's been really valuable. However, it can also be more difficult to assist participants. I can't just lean over their shoulder and see what their laptop is doing or why they're getting a weird error. And it's a little bit more tricky to do that. Our activities are occasionally easier for people to complete at home. If you'll think back to that first picture of the test bed, there are a lot of people in there and it can get quite loud and difficult to focus. But we have unexpected pitfalls that we have to deal with in the virtual world, like power outages. And then a different virtual experiment, we actually had winter weather that was very extreme and led to a delay of an experiment. So some tricky things to handle in a virtual world. So we're trying to figure out how these hybrid experiments might look. I actually talked to some colleagues this morning with some first ideas for how we might do this for 2023. But we're so up in the air and don't have this all figured out in stone so much that I actually changed the bullets here to question marks. So one option is to do a combination of virtual weeks and in-person weeks. Or we could do daily virtual components for everybody. So even if you're here in person, maybe you have to go and do some activities online. We may have things running in parallel. So we could have virtual and in-person experiments exploring similar questions. Maybe everybody gets together for a few activities and then goes and does other activities separately. Maybe we have people do some things virtually the week before they come in person. We are starting to look into exploring more of those medium range forecasts and verification, kind of out in that day 3 to 8 convective outlooks. And perhaps we can leverage virtual to generate those forecasts and then later have people verify them. So a lot of questions right now. I think it's a really exciting venue and that there are ways that we can take this experiment that will continue to be very cutting edge and really leverage the benefits of both virtual and in person. It might take us a few tries to get it right, but every year we listen to feedback and we get feedback on how to make the next year's experiment better. And I think that'll continue as long as the spring experiment goes on. So just to sum things up, what have we learned from these experiments? We have learned a lot. I have my email address up there. If you all think of a question later, feel free to email me. I love talking about the test bed. Hopefully that's obvious at this point. But our experiments give researchers the chance to test products, get feedback from operational forecasters, and the forecasters get to see what's coming down the pipeline and get to be able to generate ideas for useful things for researchers to work on. So it really does allow for this back and forth between two communities that are actually more than two communities that may not get to talk very frequently. Recent successes include the implementation of the HREF, testing of new versions of the HER before they become operationalized, and testing new forecasting techniques like those conditional intensity forecasts. Our subjective and objective verification techniques that we have combined to create a more holistic evaluation strategy. So if you have a statistic, it can potentially wash out impacts from individual cases. So by looking at cases subjectively, we're able to get this feedback that you might not be able to see if you're just looking at plots of stats. So we're really able to, again, leverage the best of both worlds to create this holistic evaluation strategy. We introduced and test new methods, new activities, new products every single year. So even if you've been to the experiment before, you're probably not going to see the same exact stuff the next year because there will be a lot of new things. And really, I just want to finish up with the keys to successful R2O and O2R research. It's collaboration, communication, well-designed tools, iteration, and perspective. I think when everybody comes in knowing that there are a lot of valuable perspectives that are going to come into play, that it turns into a really special experiment, and that a lot of growth and learning can take place in that sort of framework. Finally, I'd like to acknowledge all of my fellow spring experiment facilitators. This list is probably not even exhaustive. There are so many people that are working to make this experiment happen. And it's not just our facilitators, but also our participants for, completing all of these activities for us, and our contributors for preparing those data flows and getting data coming and talking to us throughout the whole process. The funding there is for our Cooperative Institute, but a big thanks to a huge team, and thank you all for your time. I would be happy at this point to take any questions. Thanks.
All right. Thank you very much, Berkeley, for the excellent talk. And we are going to open now for the questions. But just before that, I'd like just to acknowledge the receipt of a couple of messages of people saying that they couldn't access the Google Meet link because we had a technical decision to close the access to the Google Meet shortly after the beginning of the webinar broadcast. But still, we informed the site, the link for the YouTube broadcasts, the real-time broadcasts. So I hope people manage to also follow the presentation through the YouTube link. Okay, so now we are going to the questions. We have here in we are going to follow both the Google Meet chats and also the YouTube chats. There is a first question by, let me see if I'm getting right, is David Pichinte. The question is, how do you initiate your mesoscale model, GFS, or do you have your own analysis process for first guess?
Yeah, that's a good question, and it differs between the different models that are contributed in. So I think some of them do come off of GFS initial conditions. Some of them, like the HER, have the HER-DAS data assimilation system. Some of them are cold start models and don't utilize data assimilation. So there's an operations plan that's associated with each spring forecasting experiment from our webpage. And those have the specific details of all of the different models that are put into the experiment and would have that information for each of the models in there. So I can't remember all of them off the top of my head, so I will try to find that link and maybe get that link in the chat here at some point. It's a good question, though.
Okay. Next question, also by the same person, David Pichinte. What is or are the main variable or set of variables that you use to verify the model outputs? And then a follow-up question, how do you validate the model outputs that change in time and distribution compared to the actual data?
Yeah, that is a very good question. Series of questions. Just dropping the operations plan in the chat there. So the main variables and the set of variables that we're using to verify are that reflectivity from MRMS. We utilize the storm data reports of tornadoes, wind, and hail to verify things like updraft helicity at 2 to 5 kilometers. Same for wind reports. We'll use the wind reports to verify our severe wind forecasts, especially those measured reports. That's really helpful in getting the magnitude of the wind speeds. We occasionally do precipitation, and so we'll use stage 4 precipitation observations. And for temperature, it's more of the 3D RTMA temperature grids. So we pull from a lot of different sources, but subjectively, we mostly do radar reflectivity, storm reports that are in, and then 3D RTMA data for our environmental fields. That's really all we have time for in our evaluation period.
Okay, I do have a follow-up question again. How about Go 16 or 17 products? Are they useful for the model verification as well?
Yeah, we have not utilized those extensively. We've looked at them occasionally in some of our projects, but we actually have a satellite experiment in the test bed that's more on the experimental warning program side of things, and they really dive into those different experimental satellite products and satellite data sets, which I know are really useful in radar sparse regions, which is a huge challenge globally for forecasting the severe weather.
All right, thanks. Again, a couple of questions by David Pichinti. Could you comment a little bit more about the object verification methods?
Yes, I think that probably relates to some of the machine learning guidance and how that is their probabilities within the object. The paper that's related to that is, if you look up Flora et al., there is a machine learning paper that describes their different techniques as far as that goes. I think it's similar to the mode verification that is in the MET toolkit, in that it looks at the different orientation of the objects and the size and centroid displacement. And so I think they used that when they were doing their initial calibration of the machine learning guidance. But we don't really do a lot of object-based verification whenever we're in the testbed itself. The object-based methods are really meant to replicate the subjective verification that we do, because you can see if you've got a storm that's like in one location, and then maybe the actual storm is 50 or 100 kilometers off, but it's the right mode, it's the right speed, it's the right timing. Traditional grid-based methods will say that was not a good forecast, but a forecaster might look at it and say, the model told me there would be a storm in this region at this time, moving at this speed. That gave me some useful information. So that's really what I think a lot of the object-based methods try to get at, is what we can see subjectively.
All right. Last question by David Pichinti. HER is based on WRF or is based on its own physics?
Yes, it is a WRF-based dynamical core. So the HER is WRF-based. All of the RRFS models that I talked about today are FV3 dynamical core. So we do have a mix of WRF-based and FV3-based models in the spring forecasting experiment that we look at.
All right, next question by Marco Josevicius. With the experience of performing a hybrid in a hybrid way, I guess it's relating to the communication, the participants in a hybrid way, how do you see the feasibility of reproducing this methodology with other institutions so we can this culture in other places?
I think it's a really exciting opportunity, honestly. I feel like the virtual and the hybrid sense of things have opened things up. We have had collaborations in the past with the Met Office in the UK, and I'm trying to think if we have any others off the top of my head. We've worked with the Bureau of Meteorology a little bit in Australia, but really being able to hold these sorts of experiments and have other countries hold these sorts of experiments, I think that's very much opened by this hybrid and this virtual world. Maybe one of the main constraints, honestly, would be, can we run models over the US and over the other country of interest that we're looking at? I think it would be very cool to have a future test bed where maybe we've got, groups of modelers from different countries, and we're all running a model over the same country, and maybe we switch what country we're running over every week, and we're able to see the different performance in different regions of the globe. I think that would be something that we could do in a virtual nature. As fun as it would be for all of us to get on planes and go to each other's countries, I think that would be very cool, but it's probably not feasible, right? So I think there's a lot of opportunity here. I do want to emphasize the spring forecasting experiment has evolved over 22 years now. So it did not start out this big or this involved. And so I think, the scope and the size of what we have here is huge. And so to start replicating it elsewhere, just starting small with some of these collaborations, maybe it runs for a week, maybe it's an on-demand type thing. I think there are a lot of tools out there to be able to communicate and try to get these things spun up. I do think the limitation is probably just from a modeling perspective more so than a collaboration or a communication perspective.
All right.
It's an exciting time to be in the test beds.
And before we go to the next questions, it's just because I want to take advantage of this topic. Based on your experience, did you see any change or improvement, say, in the communication or interaction between the operational community and the research community in Norman during the periods, let's say, the off spring experiments, during the rest of the year? Did you see a change in this interaction?
Yeah, I mean, not in the last few years because we haven't largely been in the building, but I will say that, we'll be in the test bed and, the wall is glass between SPC and the test bed, and we make experimental forecasts. And sometimes forecasters will come over and look at what we've done and they'll be like, that's interesting. But one of the coolest things that happened in the test bed that was one of these interactions, not in the off season, but in the on season, was we had a high risk day in Oklahoma in 2019, May 20th, 2019. And the forecast ended up not being a giant tornado outbreak, but a lot of the guidance and a lot of the observations suggested that it could have been. And the day after, when we were reviewing what had happened the previous day, the lead forecaster from the SPC came into the test bed and talked about his decision-making process in that forecast. And it was it gave me goosebumps to hear him discuss his reasoning, his forecast practices, and to say, here's why we did what we did. And that was just a magical moment. And then after that, we're able to have researchers dive into those really interesting cases and try to explain, what went wrong in the models. Why was the HERS showing a giant outbreak of supercells? What was going on in these cases? So in the off season, you do see the researchers tackling these sorts of problems. And in the run up to the HWT too, in the collaboration of getting things ready, we'll give some feedback that says, well, you may want to adjust this because in the past we've heard forecasters comment this thing. So we do occasionally act as agents to communicate between the forecasters and the researchers, but I'm sure there are discussions that go on that, I'm just not necessarily aware of.
Right, that's great. Okay, Bruno, do you want to take over the next questions? Read the next questions. Are you there?
Yeah, I can read that.
Yeah, please.
I think the next question is from Rakesh. Is there anything related to the lightning forecast from the Mesoscale model? And could you please enlighten on that topics a little bit and any recent progress?
Yeah, that's a very good question. Our work, we don't really focus in too much on lightning when we're doing our specific evaluations. We mostly just focus on where it's going to be, those severe convective hazards. We do have some lightning data. I'm trying to remember what the lightning data is offhand, and if I have any slide that would have that on it. It is an option that you can toggle on if you don't have a lot of severe weather. In addition to the mesh and the warnings, you can put it's in here. You can also put lightning data up to see if there were storms in a specific area. But a lot of the lightning work and the lightning research has been done on more of those short time scales. And so that has been in a lot of those experimental warning program and the satellite experiments. So it's not quite in the range of what we tend to look at as far as the output goes. And so I would probably point you to those resources. They've done a lot of work on it and would be much more aware of some of the recent progress on there than I am.
Okay. Yeah, so I have a question too. Can you talk a little bit about the RRFSP2, I think that's the name you mentioned, which is supposed to replace the HRF? Yeah. Like how is it organized? Is that a one dynamic core or multiple dynamic cores and etc.?
Yeah, that's a great question. So the HREF right now has multiple dynamic cores and is that, born of the storm scale ensemble of opportunity. The RRFS is a much more formally designed ensemble. And so it is based on a single dynamical core. And there is talk of introducing some spread based on different physics parameterizations within the model, implementing stochastic physics within the model, and utilizing some different initial and lateral boundary conditions to generate the spread. But it is much more formally designed than the HREF, which is why we've been, testing in those little clouds showing all of the different experiments. Those are different ways that we're testing to introduce some spread into those formal ensembles to try to get to have some sort of the model diversity and a large envelope like we see from the HREF. So it was pretty exciting to see the RRFS perform so well in terms of the forecasts, especially when we took the names off of the models and people didn't know which one was which. And so it was really interesting to see some of those results. So I've been very impressed by the model development community. The push towards the RRFS is not that old. We've been looking at these models for a few years in the testbed, and every year the improvement that we have seen has been extremely large. And so that is all to the credit of the developers and the folks who are working to improve those models. They've been just able to do so much in a relatively short amount of time.
Right. And how many ensemble members do you have?
Yes, it is a 10-member ensemble as well.
10 okay. And it's based on the FV3?
Yes.
Oh, okay.
Yeah, it's all surrounding the FV3 dynamical core.
Right. And just a follow-up question, like what would be your recommendation for like countries that are starting to have computational resources to run convection allowing ensembles? Like, would you suggest like using one core or using multiple cores, and like, or something based on the HREF, which is a multiple core and multiple initialization times? And what's your suggestion for these countries that are starting to work with these convection allowing ensembles?
Yeah, that's a very good question. I do think time lagging is usually a good thing to include in there, just you've got different initial conditions. But the reason that there was a pivot away from the HREF or an emphasis toward more of a formalized ensemble was just because of the resources that it takes to maintain so many different cores, different code bases and that sort of thing. So if you are just starting out and you don't maybe have a huge number of people to work on the model, it would make more sense to develop around a single convective core and try to get that spread from time lagging or different physics parameterizations. We're able to get a decent amount of diversity there, and utilize some of those methods that have a similar code base so that you're not spending a lot of resources trying to develop 4 or 5 different things simultaneously. That's behind the push, and I think it makes sense from a starting out perspective. But I'm not probably the most knowledgeable person about this. I know there are a lot of model development folks who would have opinions on that as well. So as someone who sees people developing models and tests the end results, those would be my recommendations.
All right. And we have another question from Marco Josevicius. Is participation in these experiments allowed for professionals from countries other than the USA? And if yes, what's the way to apply for an application?
Yes, we have had people participate from other countries. We don't provide funding to come to the in-person parts of it, but that is why the virtual component was really nice, was because people could just join in. And in order to do that, depending on, Marco, if you're with an organization that you might have multiple people interested in participating, we reach out to the organizations. Otherwise, contacting me or contacting Adam Clark, which is adam.clark@noaa.gov. Whenever it's about February or March is when we start to cultivate the participant lists and see who all is going to be coming. And yeah, that'll be interesting because our numbers ballooned when we were in a virtual space. We weren't constrained by the number of people, so we were having up to 30 or so participants per week for the 5 weeks. So it got to be quite a few people, whereas in the physical test bed, 20 is like the upper end of comfortable, probably, for having that many people. And that was before COVID. So I don't know if people's comfort thresholds with being near a lot of people have changed.
And I think that's the last question is from Franco Villela. He says, thanks for the great presentation. And how big is your team? How many meteorologists, IT experts, computer engineers, and MLIA experts? I think it's machine related.
That's a very good question. So at the end there for those acknowledgements, I do have a lot of the different team members in putting together, in putting together the experiment. So Adam's a research scientist with NSSL. Israel is the Science and Operations Officer at SPC. Kent and Brett are both researchers and web developers. Kenzie's in social science and research. So really all of these people contribute to the Warn-On forecast system and the spring forecasting experiment. Israel is one of our main conduits and connections with the forecasters, but we also do have SPC forecasters come in and facilitate during the experiment itself. And one of these folks, Joey Pica, he actually used to be an SPC forecaster and has now shifted more over onto the research side of things. So he tends to play both roles during the experiment. So we really do have a pretty large team to make sure everything is working on a day-to-day basis. And even beyond this team, you know, we've had contact with the IT personnel at the lab that hosts the website if we're having website issues. We've got all the different people who are contributing data. So it's a huge effort by a very large number of people. Core planning and laying out how the experiment will go, it's probably closer to like 6 to 10 of us, but sometimes people will take components and they'll develop individual components during the day. So yeah, it's a big effort for sure. I also saw David's question about the paper, and yes, I think that is the correct paper to look at.
Oh, okay. Yeah, I think those are all the questions we had. Hernani, do you want to conclude the seminar?
Yes, we have just one comment by Pedro Rigori from Argentina. He gave the talk last week, and he's just said a great talk, Berkeley. Thanks. And
thank you so much. It's good to be a part of the series. Several great speakers.
Yeah, we are very, very happy that you managed to participate, and it's great also to get one message among so many important messages, but one message from your presentation: the need of investing on good ensembles on the high resolution as well. Sometimes we may feel tempted when we have high computing power to go into very high resolution, but on a deterministic mode only. But we do have to save computing power to have also ensemble on that resolution. So it's a very important point that you really emphasized in your presentation.
Absolutely. Having those ensembles and having just a different envelope of solutions and being able to give confidence is pretty crucial when you're dealing with these extreme tail ends of the distribution, for sure.
Yeah, that's great. And I do have one last question. How, if you didn't have the weather reports, okay, from storm data or the ones that you get more near real time, how bad would be your verification without the weather reports? Because this is something, it's very specific, I'd say, to the United States and a few other places around the world. You have the fact that you have access to high quality weather reports in so many countries, we don't have that available.
Yes.
So I have to make this question.
No, it's a very good question. And I thought about that as I was putting together this talk and looking at all of the data sources. I kind of felt a little spoiled by having so much data for us to look at subjectively. I think in those cases, you could really leverage a lot of those satellite observations. There's some current research that's been done at the School of Meteorology that looks at the signatures from cloud tops that are indicative of extremely severe storms, that cirrus that comes off of the anvil of the most severe storms. And so potentially we would utilize that after the storm passes. Sometimes, you can see hail fall. So I think we'd have to get very creative with that and with lightning detection. And I don't know if there would be any possibility also from the satellites to get observations of maybe where a forest was hit and seeing actual damage from the storms after the storms pass. So it would be challenging, but I think some of the new satellite instrumentation that is in place would be absolutely crucial if we didn't have the data sets that we currently have here. But I know radar, I would say radar too, but I know radar can also be quite sparse in some regions. But yeah, radar would be another good way to go about it. And we use that in lieu of some of those observations when they haven't quite come in yet.
All right. Well, thank you very much, Berkeley. Really great talk. And we would like to remind everyone that this talk will be is recorded, so you'll be able to access again, or to you can share the link, or the YouTube link, with other people who may have missed the presentation. And one month from now, we're going to have another talk by Petra Gronemeyer from the European Severe Storms Laboratory. And so again, Berkeley, thank you very much for participating. We are very happy. It was a really great talk. And I'd like also to thank all the questions from all the participants.
Yeah, they were great. Thank you all. And if you think of one, feel free to let me know and email me.
Okay, all right. So once again, thank you everyone, and have a great weekend. Okay, bye.